Now again with this example, if you haven't read through it and a few times and got a good understanding of what's going on, then understanding the relevance between the written and the diagram, then please, if you haven't done that, please stop the video and take some time to do that before you start listening to the solution. So what I'm going to do is I'm going to isolate 3 key triangles and draw them and put the data on them and then work from there. So you can see there that I've started with a triangle from the original sighting. So from this position up to the balloon was an angle of 78 degrees. We don't know the distance on the ground directly under the balloon. We do know that the balloon is flying along at a constant altitude of 3,000 metres, so the distance above the ground is 3,000. And anything vertical, it will make a right angle to the ground. So we've got a right angle triangle there. The second triangle represents 20 minutes later, and you can see we still have an altitude of 3,000 metres, an angle of elevation now of 73 degrees. We still have a right angle triangle because directly under the balloon would be the point of 90 degrees to the ground, and we don't have the distance from the observation point to underneath the balloon, but you can see that I've highlighted that in red because the third triangle is the triangle on the ground, which actually contains the angle that we're asked to find. So there was the observer was here at this point. They looked out initially, saw the hot balloon, and then rotated through this angle and observed the balloon 20 minutes later. So here's our triangle. Highly unlikely to be a 90-degree triangle. We know very little about it. We don't know the size of the angles. We don't know the distances. However, it would be possible to find the distance that the balloon has actually travelled, and keep in mind that this dotted line actually would be equivalent to the distance that the balloon has actually travelled above the ground. And to calculate that distance, we can use the formula distance is equal to speed times time, and that will give us at least one side of our triangle. Now, do not assume that this is 90 degrees and that's a hypotenuse, although it might look like it. We can't do that. So you can see there 950 metres per hour. So time has to be in hours. 20 minutes is 1/3 of an hour. And we get then a distance in metres of 316 2/3. So the length of that side of the triangle is 316 2/3. When you think about this triangle, it's looking awfully like we will use the cos rule because we're finding an unknown angle, and should we be able to find the side that I've drawn in green here and the second side in red, then we would have all 3 sides and finding an angle. So at this stage I'm thinking cosine rule. But to get to that, we have to be able to find the green side and the red side. But if you look at these 2 triangles, you will simply use your right angle triangle trigonometry to do that in both cases. I'll write that up now. From the first triangle, we'll use the tan ratio, and we'll get that x is 3,000 on tan 78. Now you can leave it as that, or you can go to your calculator and maybe go to 4 or 5 decimal places. I'm just going to leave it as that. Go to the second triangle. Similarly, you use the tan ratio, 3000 on y. Y is 3000 divided by tan, 73. Now, so that I'm going to leave it in that form so that I get as accurate an answer as I possibly can. And using my cosine rule, which is the cos of the angle is equal to a squared plus b squared minus c squared all over 2ab. So the actual angle is cos inverse of that calculation. It looks pretty messy, but it sits here on the calculator. It's all there underneath that, and it brings up 44.45 degrees, which to the nearest degree is 44 degrees. So provided I haven't made any mistakes with some basic trig there, really you can see that all the calculations do really just go back to some basic trig work. So you should be right now to do questions from 2G and H.